Welcome to the lecture for section 7.1, Solving Trigonometric Equations with Identities. By the end of the lesson, you'll be expected to verify identities and simplify trigonometric expressions using different identities and algebraic techniques. Now, this is a quick review of fundamental identities. Most of these should look familiar to you by now, since we've discussed them all in previous sections, but now we're going to gather them all in one place by category. Let's start with the reciprocal identities. We know that cosecant of theta equals 1 over sine theta. So sine theta equals 1 over cosecant theta. Secant theta equals 1 over cosine theta, which tells us that cosine of theta is 1 over secant of theta. Finally, cotangent of theta is 1 over tangent of theta, and tangent of theta is 1 over cotangent of theta. Next, quotient identities. Tangent of theta is sine of theta over cosine of theta, and cotangent of theta is cosine of theta over sine of theta. Next, we have our even-odd identities. So sine, the sine function is odd because sine of negative theta is equal to negative sine of theta. This tells me that its reciprocal function, which is cosecant of negative theta, is also odd. Cosine of theta is even, so this will just be cosine of theta. So secant of negative theta must also be even. Finally, we have tangent of negative theta is going to equal negative tangent of theta, since tangent is an odd function. And cotangent of negative theta equals negative cotangent theta. Finally, we have our Pythagorean identities. This main one, cosine squared theta plus sine squared theta equals 1, is what you should memorize. These next two can be derived from this one identity. If you have trouble deriving these, then memorize all of them. 1 plus tangent squared theta equals secant squared theta. And cotangent squared theta plus 1 equals cosecant squared theta. And so, quick warning, you do need to memorize these. Let's look at our first example. Example 1, verifying trigonometric identities. Verify that sine of theta times cotangent theta equals cosine of theta. Let's start with our left-hand side. So this is the left-hand side, and this is the right-hand side. And typically I tend to start with whichever side has more going on. If you notice, this is just a cosine theta. There's not much to simplify, but here I'm given a sine theta and a cotangent of theta. This is why I start with the left-hand side. So sine of theta times cotangent of theta equals sine of theta times what? How can I rewrite cotangent of theta? If you said cosine of theta over sine theta, you're correct. If you notice, I have a sine in the numerator and a sine in the denominator. Well, anything divided by itself is just 1. So we're left with cosine of theta, and we're done. Once we've shown that the left-hand side is equal to the right-hand side, we have verified the identity. Let's look at part B. And again, I'm going to start with the left-hand side. So I have 1 plus sine of x times 1 plus sine of negative x. Sine is an odd function, so this should be a negative side. That means this whole left-hand side is equal to 1 plus sine of x times 1 minus sine of x. This is a difference of squares, so this is 1 squared minus sine x squared, which I can rewrite as 1 minus sine squared x. Now, using the fact that cosine squared x plus sine squared x equals 1, we can rewrite this by subtracting sine squared x from both sides to end up with cosine squared x equals 1 minus sine squared x. Now I have a 1 minus sine squared x here, which is exactly what I have here. So this whole thing becomes cosine squared x. If you notice, we have managed to derive the right-hand side starting only with the information on the left-hand side, so we're done. Let's turn to the next page. Part C, we want to verify that sine squared alpha minus cosine squared negative alpha, this entire quantity divided by sine negative alpha minus cosine of negative alpha, is equal to cosine of alpha minus sine alpha. And this is the Greek letter alpha, not a lowercase a. Don't confuse those, please. Let's start with our left-hand side. We have sine squared alpha minus, and notice here I have a cosine squared negative alpha. What can I do with this negative? It does go away if you said that you're correct, because cosine is an even function. So this becomes sine squared alpha minus cosine squared alpha. Now what about down below? Sine is odd, so this becomes negative sine alpha minus cosine of alpha here because cosine is even. Next, notice that this in the numerator is a difference of squares. It is crucially important that you recognize what these are, as I've said earlier in other videos and often in class. So we can rewrite the numerator as sine of alpha minus cosine of alpha times sine of alpha plus cosine of alpha, and divide this entire quantity by negative sine alpha plus cosine of alpha. Notice all I did there was factor out the negative in the denominator. So let's keep going. We have something that matches here and here. So those go away since anything divided by itself is just 1. And we end up with sine of alpha minus cosine of alpha divided by negative 1, or cosine of alpha minus sine of alpha. And here we are done since our left-hand side was manipulated into our right-hand side. Let's look at part D. Verify that cosine of x times tangent x minus secant of negative x equals sine x minus 1. So looking at the left-hand side, we have cosine of x times tangent of x minus secant. And secant, is that an even or odd function? Secant is even, so this just becomes secant of x. And I can rewrite this as cosine of x. And here I have sine x over cosine of x minus 1 over cosine of x. So this becomes cosine of x times sine x minus 1 over cosine of x. If you notice, we have a matching pair in the numerator and denominator. And since we have these factors in common here, cosine of x divided by cosine of x is just 1. So we end up with sine of x minus 1. And we are done. Let's look at the next example. Fully simplifying trigonometric expressions using fundamental identities. Use the fundamental identities to fully simplify 3 sine cubed t times cosecant t plus cosine squared t plus 2 cosine of negative t times cosine of t. So we start with writing down what we have. 3 sine cubed of t times cosecant of t plus cosine squared t plus 2 cosine of negative t cosine of t. So this becomes 3 times sine cubed of t. What is cosecant? How can I rewrite cosecant as a reciprocal of some other trigonometric function? If you said 1 over sine of t, you're correct. Then we add cosine squared of t plus 2 times. Now cosine of negative t, how can I rewrite that? If you said cosine of t, you're correct. Times cosine of t. So we have 3 sine squared t plus cosine squared t plus 2 cosine squared t. That's because cosine t times cosine of t is cosine squared t. So this becomes 3 sine squared t plus 3 cosine squared t. Both terms have a 3 in common, so let's factor that out. And what can I do here? Sine squared of t plus cosine squared of t. That's the basic Pythagorean identity. That's just 1. So this is 3 times 1, which is just 3. And at this point, we can't simplify any further. Let's look at example 4. Let's verify that tangent squared phi divided by secant squared phi equals 1 minus cosine squared phi. Note, phi is not the same thing as theta. These are different Greek letters. This is phi. This is theta. Do not interchange them in your work. So beginning with the left-hand side, we have tangent squared of phi divided by secant squared of phi equals tangent squared of phi times 1 over secant squared phi. Tangent can be rewritten as sine squared phi over cosine squared phi, and secant squared is 1 divided by cosine squared phi. So this becomes sine squared phi over cosine squared phi times cosine squared phi over 1. Again, we have factors in common in both the numerator and the denominator. So these become 1, and we're left with just sine squared phi. Using the Pythagorean identity, the basic one, this is equal to 1 minus cosine squared phi. Let's turn to the last page of this section. Part E, secant x plus tangent x divided by sine x equals cosecant x divided by secant x minus tangent x. Let's verify this. And I've been working with the left-hand side a lot. So for this one, I'm going to start with the right-hand side. In this case, both sides have ample opportunity for simplification, so you could choose either. In most cases, but in this one, it's a lot easier to choose either side. If you notice, the numerator on the left-hand side and the denominator of the right-hand side are conjugates. So I'm going to start off by multiplying the numerator and denominator of the right-hand side of cosecant x divided by secant x minus tangent x by this conjugate here. So secant x plus tangent x divided by secant x plus tangent x. So in my numerator, I end up with cosecant of x times secant of x plus tangent of x. In my denominator, I end up with secant squared x minus tangent squared x. Again, another difference of squares. Let's rewrite this all. How can I rewrite secant using one of the fundamental identities? That is a version of the Pythagorean identity. If you recall, secant squared x equals 1 plus tangent squared x. So without any manipulation, we can replace this secant here with everything on this right-hand side. So we end up in our denominator here with 1 plus tangent squared x minus tangent squared x. In my numerator, I have 1 over sine x times secant x plus tangent x, quantity divided by 1. Remember, you can rewrite anything as a fraction by putting a 1 in the denominator, and all I did here is I used the reciprocal identity to rewrite cosecant of x as 1 divided by sine x. So in our denominator, we have 1 plus tangent squared x minus tangent squared x. These are going to add to 0, and so I will just end up with a 1 in my denominator. In my numerator, I have secant x plus tangent x divided by sine x. So this ends up being secant x plus tan x divided by sine x. Since we managed to derive the left-hand side starting only with the right-hand side, we're done. Let's look at the next example. Example, writing one trigonometric expression in terms of a second. Write the following identity in terms of cosecant x. So we want to rewrite this so we end up just with cosecants. So let's start. We have 1 over 1 minus cosine of x minus cosine of x divided by 1 plus cosine of x. In order to add and subtract fractions, we need to have a common denominator. So let's go ahead and do that. What is our common denominator? I have a 1 minus cosine x here and a 1 plus cosine x here. So let's multiply both sides by the missing piece. So we're going to multiply both by their conjugates. Multiply this side by 1 plus cosine x, this side by 1 minus cosine x to get the appropriate denominator for simplifying this fraction. So what does this give me? I have 1 times this numerator is just 1 plus cosine of x. In my denominator, I'll have 1 minus cosine squared x. Since we multiplied conjugates, we end up here. This is a difference of squares. And then after the minus sign, I'll have minus cosine x, 1 minus cosine x here, divided by 1 minus cosine squared x. So let's keep going. I have 1 plus cosine x minus cosine x plus cosine squared x. If you notice, all I did was multiply cosine of x times 1 times this negative is negative cosine x. Then here I have a negative times a cosine times a negative cosine x to get a positive cosine squared x. And in my denominator, 1 minus cosine squared of x can be rewritten as sine squared x. So this becomes 1 plus cosine squared x divided by sine squared x. Of course, we can write cosine squared x again as 1 minus sine squared x. And this is just an application of the basic Pythagorean identity. Let's split this up. We'll rewrite and split this up. We have 1 plus 1 is 2 minus sine squared x divided by sine squared x. So we have 2 over sine squared x minus sine squared x divided by sine squared x equals 2 cosecant squared x minus 1. Now we're done. We have no other trigonometric functions except cosecant of x, which is exactly what we wanted. Let's look at the last example for today. True or false identity. Determine whether or not the following identity is true or false. If it is false, find an appropriate equivalent expression. So here I'm going to start with the left-hand side because the right-hand side only gives us a secant squared to work with. So I have secant of theta plus tangent of theta divided by cotangent theta plus cosine of theta. I'm going to rewrite everything. So secant is 1 over cosine theta. Tangent is sine theta over cosine theta. And then I have cotangent is just cosine of theta over sine theta plus cosine of theta. And to get a little ahead, my denominator here is sine of theta, so I'm going to go ahead and multiply the numerator here, sine theta, and the denominator by sine theta as well. So I end up with 1 plus sine theta divided by cosine theta, this quantity completely in my numerator. In my denominator, I have cosine theta plus cosine theta sine theta divided by sine theta, completely in my denominator. So this is 1 plus sine theta divided by cosine theta times sine theta divided by cosine theta plus cosine theta sine theta. We can factor this denominator here. So I'm going to leave the fraction on the left untouched as 1 plus sine theta divided by cosine theta. But this fraction here I'm going to rewrite as 1 plus sine theta times cosine theta. Notice all I did here was factor out this cosine of theta. So let's keep going. I have a 1 plus sine theta in my numerator and 1 plus sine theta in my denominator. Anything divided by itself is just 1. So we end up with sine theta over cosine theta times cosine theta, which can be rewritten as 1 times sine theta over cosine theta times sine theta, cosine theta, which is 1 over cosine theta times sine theta over cosine theta, or secant theta tangent theta. With that, let's look at what we should have gotten. This problem is stating that this whole left-hand side equals secant squared theta. We can confidently say this is false, and the expression on the right-hand side should be secant times tangent. This concludes the lecture for section 7.1.